In double hashing, we use two hash functions. One hash function is our original function that we discussed, something like key &7. Then one more hash function to find the next slot while we are probing for a free slot. In quadratic probing, there was this issue that you need to have double size to ensure that you find a free slot, and M should be prime. So these two were requirements there in the quadratic probing. In double hashing, if your M is relatively prime to this S2 function, then you do not need double size. If there is a free slot, you will always get one. That's the big advantage of double hashing compared to quadratic probing. Also, it avoids clustering. In quadratic probing also we had secondary clusters, right, which are not there in double hashing. We'll soon do an example of double hashing to understand these things, this point, and also we'll understand how these two hash functions work together. Also, since there are no clusters formed, this distributes your keys more uniformly compared to linear probing and quadratic probing. Let us do this example to understand double hashing. In this example, I have considered M as 7, the value that we have been using in all the examples. Our H1 function, the first function, is key &7. S2 function, which is used when collision happens, is 6 minus key &7. Why a function like this? This is an important thing about this function. Your H2 function should never return 0, because if it returns 0, then you will keep probing the same location again and again. Some location returned by this function is, say, here 2. A collision happens, you will put I equal to 1, and if this function returns 0, this whole value is going to be same again. So we will keep probing the same location. So that is why we design this function this way. Your key &6, it returns values from 0 to 5. You subtract those values from 6, so you get values from 1 to 5. So you get values from 1 to 6. Let us do this example. Let's try to insert these values in our hash table. So when you insert 49, you use your first hash function. This is something you use when you see a collision. Or you can say first time you put I equal to 0, right? So what will happen? You will put 49 here, no collision. 63, collision happened. Now you will not simply use H1 key, you will find the next location using H2 key also. So let's compute the H2 key. For 63, this is going to be 6 minus 63 &6, which is going to be 6 minus 3, which is going to be 3. I is 1 because this is the first time we are trying to handle the collision. And what is H1 key? H1 key is 0. So we'll do 0 plus 1 into 3 &7. So what do we get? We get 3. So we put 63 into the slot, right? Let's try to put the next value, 56. So I've intentionally taken some values which cause collisions so that you get an idea how collisions are handled by double hashing. So this value is actually 7. Let's put 56, we'll get 0, right? So H1 key is 0. What will be the value of H2 key? 6 minus 56 minus &6. So what will be this value? 6 minus 2. So you will get 4. And you will put 1 into 4 &7. So what will you get? You will get 4. So you will insert 56 here. Now 52. What will you get when you do 52 &7? You will get, let's rub this part. So 52 mod 7 is 3. So you will go to location 3 and try to insert, but location 3 is already occupied. So you will handle the collision for 52. You will compute H2. So you know H1 key is 3. you will now compute H2 key. So it will be 6 minus 52 mod 7, 6, which will be 6 minus 4, right, which will be 2. So it will be 3 plus 2 ampersand 7, which will be 5. So 52 you put at 5 location. You can see that it's working much better than, linear probing. We have found only one collision every time so far, right? And we have filled almost half of the table, and there was one place for which we had many keys. Let's do more exercise. Let's put the next value, which is 54. So for 54, what is the value of H1 key? It's 5, right? H2 key, 6 minus. So H1 key I'm computing using this formula, right? Key ampersand 7. 54 modulo 7 is 5. H2 key is 54 modulo 7, 6. So it's 0, right? So it is going to give you 6. So it's going to be 5 plus 6 modulo 7, which is going to be 4. This time we see another collision. What do we do now? We multiply this 6, the value that we got, with 2 now. So what do we get now? 6 into 2, because this is the second probe. We got a collision, now we are trying the second time. So I just changed the value of I. H2 key is going to be same, right? Because we are going to insert the same key. So this time what do we get? 17 modulo 7, which is 3. So we see a collision again. So we put the value 3 now. What do we get now? 6 3 is 18 plus 5, 23 modulo 7, 2. This time we find a free slot. So we insert this value 54. We could insert after the 3 collisions. Let's try inserting 48. What do we get as 48 modulo 7? 6. And 6 slot is available. So we insert 48 here. So this is how double hashing works. Now let's try understanding this requirement of double hashing that we discussed, that H2 key and M should be relatively prime. What is the purpose of this? What are we doing when we were seeing collisions? So let me write down what we are discussing. Y, H2 key and M should be relatively prime. We discussed this requirement in the first point of double hashing. We mentioned that if they are relatively prime, then your double hashing will always find a free slot if there is a free slot, right? What it means, it fulfills the requirements what linear probing does, right? Because linear probing goes to every slot one by one and it will find a free slot if there is a free slot. But this thing was not happening with quadratic probing. In quadratic probing, we were saying that if we have double the size, then it will find a free slot, right? Although we did not discuss the proof, we did not discuss the idea in quadratic probing, but let's get an idea here in double hashing. So what is the idea of it? We are saying that if H2 key and M are relatively prime, then we'll always find a free slot if there is a free slot. I have taken an example here to explain the concept of relatively prime. I have assumed the H2 key value here as 6. Please remember, H2 key basically tells you the shift that you need to make from the current location, and that shift is under modulo M. So I have just computed all the shifts returned by this key value when you see multiple collisions. So when you see the collision first time, it will tell you to shift by 6. If you see the second collision, this position is also occupied, it will tell you to go to slot number or shift by 5. Shift this H1 key by 5. In the next time, 3 into 6 modulo 7 is 18 modulo 7, which is having value 4. So it will tell you to shift to location 4. 4 into 6 modulo 7 is 3. It will tell you to shift to location 3 if this position is also occupied, if the shift is also occupied. Next time 2, next time 1. So you can see here it is actually telling you all the possible slots. So if there is an empty slot, it will tell you that slot. The reason for this is this value 6 and this value 7, they are relatively prime. You can try more examples. For example, if you try 4, what will you get? 4 into 1 modulo 7, 4. 2 into 4 modulo 7, 1. 3 into 4 modulo 7, 5. And if you keep doing, you will get all the numbers from 1 to 6. And if your table size is 7, then 6 are the total remaining slots, because first slot you already tried and this was occupied. That is why you are following this probing sequence. Let us take a look at this algorithm of double hashing to understand it better. We have a key to insert. If our table is already full, then we return error. Otherwise, we initialize our first position where we want to insert the key as H1 key and our offset as H2 key. So whenever we see a position occupied, we will keep on adding this offset, right? So when you are adding it, basically when you add it once, when you see first collision, you are doing 1 into offset. When you add it twice, so offset is added one more time, so it becomes 2 into offset, right? So this is a simple idea. While table probe is occupied, you do probe equal to probe plus offset modulo m. And mainly you are adding offset once for the first attempt. So if offset is already added once, when you are coming second time, it's already added twice, so you are adding third time when you are coming third time. When you find a free slot, you put this key, this is key, you put this key at that free slot, right? That's what you do at the end. If you look at linear probing is simply where offset is 1. That's what linear probing is, right? Where your offset is simply 1. So you can see double hashing as a generalized version of linear probing. If your hash function simply returns 1 all the time, then this code becomes linear probing code. Let us do a simple analysis of double hashing. Let's analyze it considering the search operation. So how will the search work? We just wrote a pseudo code for insert. How will the search algorithm work? Search will work same as insert. You will go to a slot, right? And if you find your key there, you will immediately return true. If that slot is empty, then also you will return true because the slot is empty. If you find that slot occupied, then you will use H2 key function, right? And you will use in the same manner. First time you will look at 1 into H2 key. Next time you will look at 2 into H2 key. If 1 into H2 key is occupied, right? If 2 into H2 key is also occupied, then you will look at 3 into H2 key. So search is going to work similar to insert that we discussed. Let us analyze unsuccessful search in particular. Unsuccessful. So when do we say that a search has stopped unsuccessfully? When you have either traversed through the whole table or you ended up with an empty slot, right? When you end up on an empty slot, then you say my search is over. This is an empty slot. I could not find the key till this point. If key had been there, it should have been there at this empty slot. Let us analyze this, making this assumption that our probe sequence randomly finds a slot where your key should be placed, right? That's the assumption we are making here, right? Every free slot is equally likely to be picked. I think we remember this term load factor alpha. It's the number of keys present in your hash table and your hash table size. And for open addressing, your alpha must be less than equal to 1, right? In quadratic probing, it should be at most half, right? But there is no such requirement in universal hashing. Universal hashing is similar to linear probing. It says that it should be at most 1. Now say alpha is 0.8, which means 80% of your table is occupied and 20% of your table is free. 20% of your slots are empty slots. So when you are searching a key, in how many iterations on average you will find an empty slot? 20% of your slots are empty slot, which means 1/5 of your slots are empty slots. So you will take 5 iterations on average. You will probably find 4 occupied slots and then you will find a 5th empty slot. So if your alpha is 0.8, then your expected number of trials for unsuccessful search is 5. If your alpha is 0.1, 0.9, I'm just trying to give you an intuition what should be the number of probes for an unsuccessful search. And if you have guessed it already, that's great. If your alpha is 0.9, if your 90% of your table is occupied and 10% of your table is free, how many searches you will take to reach one of those 10% slots? You will first find, probably on average, you will find 9 occupied slots and then you will find the 10th free slot on average. So for 0.8, your expected number of probes required for unsuccessful was 5 and here it is 10. Can you guess the expression here? It will be 1 upon 1 minus alpha. 1 minus alpha is the fraction of the table which is empty. So you will find one of those empty slots with these many expected number of trials. If you compare open addressing with chaining, then this does not look really great. As alpha tends to 1, it tends to infinite. It's going to become 1 minus 1, 0, infinite. Even with 0.9, you are going to have 10 comparisons if your load factor is 0.9. If your load factor is 0.99, then you will have 100 number of comparisons on average, which is a big number. We'll do a thorough comparison of open addressing and chaining in the next video.